Hey everyone, and welcome. Every single dataset, no matter how big or small, has a story locked inside it. But here's the thing. Those stories are written in the language of numbers, which can feel, well, a little intimidating. So today, we're going to build a toolkit to help us become fluent translators. Just think about it for a second. Your data is constantly talking. It's whispering secrets about your customers, about how things work, maybe even about brand new discoveries. So the big question is, are you equipped to actually hear what it's trying to tell you? So in this explainer, that's exactly what we're going to do. We're going to put together a foundational analyst's toolkit. We'll walk through 3 really powerful sets of statistical tools that will help you go from just staring at data to truly, deeply understanding it. So grab your virtual magnifying glass and let's dive right in. All right, first up in our toolkit, we've got the t-tests. Think of these as your go-to comparison set. Anytime you need to compare the average of one group to another, or even just to a specific number, this is what you'll reach for. It's your go-to when you need to spot those really meaningful differences. Okay, let's kick things off with the simplest case. A student is convinced the average grade on an exam is an 87, period. We take a sample of 36 exams and find the average is actually 83.96. I mean, that's close, right? But is it statistically different? The one sample t-test gives us our answer. We get a p-value of 0.137. Now, what's a p-value? It's basically the probability of seeing these results if there was no real difference. Since our p-value is way bigger than the standard cutoff of 0.05, we just can't say there's a significant difference. The story here? We don't have enough evidence to prove the student wrong. Okay, that was one group against a number. Pretty straightforward. But what happens when you want to compare 2 completely separate groups? Let's say we have data for US workers and German workers. The research question is simple: do they work different hours? This sounds like a perfect job for an independent samples t-test. But hold on, before we can just run the test, there's a really crucial check we have to do first. And this right here is such a critical point for any analyst: assumption checking. You can't just throw any old test at your data and hope for the best. In this case, we have to check if the spread of the data, the variance, is equal in both groups. Turns out it wasn't. And this is huge because it means the standard student's t-test, it's the wrong tool for the job. We have to use something called Welch's t-test, which is built for exactly this kind of situation. The result? A p-value of less than 0.001. The data story is loud and clear. Yup, US workers have significantly longer work weeks. Okay, so we've compared one group to a number and 2 separate groups to each other. Now, for our last t-test, let's look at a before and after scenario. A company rolls out a new bonus plan, and they want to know, did it work? Did it improve sales? We measure sales for 6 people before the bonus, and then for those same 6 people after. This is a textbook case for a paired samples t-test. And the verdict? A p-value of 0.5 and an effect size of 0. The data says the bonus had no significant effect whatsoever. Sometimes the biggest story is that, well, there is no story. Nothing changed. All right, so we've got a handle on comparing averages. That's awesome. But what about relationships between categories? Things like smoker versus non-smoker or type of illness? For that, we're going to pull out the next tool from our kit, the chi-square test. This is our relationship finder. So let's jump into a case study. We're looking at 300 people sorted by smoking status and their type of illness. The big question is, are these 2 things related or are they totally independent? So we run the chi-square test and bam, we get a p-value of less than 0.005. That's tiny. That's our signal to reject the null hypothesis. It's telling us loud and clear, smoking status and illness are not independent. There's a real relationship here, but what is it? So how do we actually find the story here? This is where it gets really cool. The secret sauce is comparing what we actually saw in our data, the observed numbers, with what we would have expected to see if there was totally no relationship at all. For instance, we observed 60 smokers with emphysema, but we only expected to see 48. It's that gap, that space between what we saw and what we expected, that tells the story. And to make this super clear, let's use a delicious analogy. And to really nail this down, I've got to share Dr. Buller's fantastic analogy. Imagine you're expecting 10 momos, right? But then the plate comes and you observe 15. You're thrilled, right? That's a happy, positive relationship. It's that simple. When what you observe is way more than what you expect, it's pointing to a strong, positive connection. That is the core logic of the chi-square test. Okay, our toolkit is really starting to fill out. But what happens when you need to compare the averages of more than 2 groups? I'm talking 3, 4, 5 groups at once.
For this job, we need to bring out the big guns, ANOVA, which stands for Analysis of Variance. This is our group investigator.
Now, you might be thinking, hey, why can't I just run a bunch of t-tests between all the different pairs of groups? And that's a great question. Here's the problem. Every single time you run a test, there's a small chance you'll find something just by coincidence, a false positive. You do that enough times, and you're practically guaranteed to find a difference just by pure dumb luck. ANOVA is the smart solution. It checks for any difference among all the groups in one single powerful test, and it keeps that error risk nice and low. And to really get how ANOVA works step by step, we're going to use another amazing analogy from Dr. Bowler, the murder mystery. So think of the main ANOVA test as the very first step of an investigation. It's that moment the detective shows up and finds a body. And the first, most important question is, was this a natural death or was something unnatural going on? So in our case, we're looking at 4 different employee productivity programs. We run the ANOVA test, and it gives us a p-value of less than 0.01. That is our verdict. This was an unnatural death. It tells us there is a significant difference somewhere among these 4 programs. But here's the catch, the mystery. ANOVA doesn't point a finger. It doesn't tell you who the killer is. It just screams, a crime has been committed. We know one of these programs is different, but we have no idea which one. So to solve this mystery, we've got to perform the postmortem. In stats, we call this a post hoc test. This is the detailed forensic work that happens after the initial finding, and the results of our investigation are crystal clear. Program C is our killer. It leads to significantly higher output than all the others. The mystery is solved, and the full story has been revealed. Wow. Okay, we've just packed 3 super powerful tools into our toolkit. So before we wrap up, let's do a quick rapid-fire recap of the core ideas, the Analyst code, that makes all of this possible. First up, the null hypothesis. This is always your starting point. Basically, it's the prove it assumption. It says nothing's happening, there's no difference, no relationship, everything is just status quo. And on the flip side, you've got the alternative hypothesis. This is our theory. It's the claim that, yeah, something is going on here. There really is a difference, or there really is a relationship we need to pay attention to. So how do we decide between the two? That's where the p-value comes in. Think of it as your evidence score. A really small p-value means your data looks super weird if the nothing's happening idea is true, and that gives us the confidence to reject it and say something interesting is going on. Then there's alpha. This is just our line in the sand. We usually set it at 0.05. It's the amount of risk we're willing to accept of being wrong and saying there's an effect when there isn't one. If our p-value is smaller than our alpha, we call it a win. It's statistically significant. But, and this is so important, statistical significance isn't the whole story. You also need to look at effect size. This tells you the magnitude of the difference. Effect size gets to the heart of it. It answers the so what question. How big is this difference really? Does it actually matter in the real world? And there it is. T-tests for comparisons, chi-square for relationships, ANOVA for investigating big groups, plus all those core concepts that tie it all together. This is your foundational Analyst's toolkit, ready to go. So, you've got the tools. You know the language, you know how to listen to what your data is trying to tell you, and to uncover those incredible stories hidden deep inside the numbers. The only question left is, what stories are you going to uncover?